Today we're going to start, or tonight I should say, we're going to start chapter 10. Chapter 10 deals with circles. So hopefully we know the basic definitions of circles, and we're just going to explore, a little bit more with what circles actually have involved with them, in terms of finding different side lengths in a circle or different angles within the circle. So you should have your guided notes that we handed out yesterday, or today, I should say. So as we go along with this video, make sure you're filling in the definitions, the theorems, you're drawing the pictures, you're working through some examples. And if you have your book, you can certainly reference that as well. Make sure you write down any questions that you have as we're going through the notes and you're watching the video, because we'll address those questions in class tomorrow. Okay, so just a quick overview. So don't mind this recording. Let me see if I can move this. Quick overview. Hopefully we know what a circle is. Just know that it's the set of points that are all the same distance away from the center. So that's where it says the equidistant from a given point. Okay, so then we need to talk about interior versus exterior. Just knowing interior means inside, exterior means outside. So if I draw a little point right here, we can label that A. A is on the interior of the circle C, and then I can put a point on the outside, and then I would say that point B is on the exterior of the circle. So hopefully that makes some sense. Okay, so then we got to talk about one definition that hopefully you know what it is, and then a couple maybe that you don't. All right, the radius, that's from the center to the circle, and then the diameter is from the opposite ends of the circle, but it has to go through the middle. So the diameter of this circle is df. And then the radii, well, actually we have three radii. We have AD, AF, and AE. Those are all radii of our circle. Those would all be the same length. So we could actually even mark them congruent if we wanted. The one piece that you might not know about would be a chord. So a chord is a segment with its endpoints that lie on the circle. So here, that would be BC. Now, if you think about it, if a chord has two endpoints that lie on the circle, a diameter is also a chord. Okay, so we can say that all diameters are chords, but I can't say that all chords are diameters. So kind of know how they relate. Okay, now we're going to move on to a few newer definitions. We kind of bring in, they sound like trig functions, but they're not. We bring in what's called a secant or a tangent line. Okay, so a secant line is a line, a segment, or a ray that intersects our circle at 2 points. So you just need to understand that a secant hits the circle twice. Okay, so this top line here that I'm highlighting in red, that's the secant line because it's hitting the circle, it's intersecting the circle twice. Okay, and then a tangent line, which is going to be in green, a tangent line is only going to intersect the circle once. So this is the bottom line. As you can see, it only hits the circle at 1 point. Okay, so make sure you know the difference between what a tangent line is and what a secant line is, and you're able to draw that. I'm going to give you an example, okay? All right, so a couple more pictures with tangents. Okay, a common tangent, when something is in common, it shares something, right? So a common tangent is going to be a tangent line that two circles are going to share. So the tangent is still only going to hit each circle once, but it's going to hit two different circles. So up here in blue, you see that as I drew that line, I'm only hitting each circle once. okay? And it's a common external tangent because if you think about it, we're outside of the two circles, so we call those external tangents. But then if we want common internal, these lines here are intersecting the circles still once, and then they actually intersect each other in between the two circles. So we kind of say that they're in between, the tangents are in between the two circles, therefore they're internal tangents, okay? And then a point of tangency is just going to be that common point between a tangent line and a circle or two circles. Anything that they're only intersecting one time. That's the point of tangency because tangent means one. Okay, so here's an example of tangent circles, two circles that intersect each other only at one point. Okay, so feel free to pause this at any point to get these written down. Okay. All right, so of course we're going to have different theorems throughout this chapter. There are going to be a lot of them. Okay, and on the come test time or quiz time, you're not going to have any of these formulas, so we've just got to start memorizing these now. So make flashcards or do something, okay? So, oh, we forgot about congruent circles. Okay, congruent circles. To be congruent, we have to be the same size, right? We have to be the same thing. So congruent circles just have to have the same radii or the same diameters in order to be congruent. And then we need to talk about what's called a concentric circle. Concentric means I have the same center. So how I would draw this is I'd have two circles, one inside of the other, and the thing that has to be true about concentric circles is just that they have the same center, okay? Their diameters and their radii are going to be different because if you think about it, if I have the same center and I have the same radii, they're going to be the exact same circle. So we can be proportional, if that makes sense. Okay, just can't be the same radii. Okay, here is the first theorem we need to talk about, Theorem 10.1. This one says if a line is tangent to a circle, then it is perpendicular to the radius at a point of tangency. So what we have here is we start with the line. Okay, so we have, or in this case, it's the segment CD. We have that segment that's tangent to the circle at B. Okay, so what I have to start is what's in red. Okay, it's tangent. So then it says, then it's perpendicular to the radius. So then CD is going to be perpendicular to AB. Okay, so then what I get, being perpendicular to the radius, is in blue. Okay? So on your note sheet, I want you to rewrite that, but please put it in your own words. Okay, and then draw the picture to where it's going to make sense to you. Okay? Theorem, and I'll come back to these examples. Theorem 10.2. This one says if you're in a plane, the line is perpendicular, or if the line is perpendicular to the radius of a circle, and its endpoints, or the endpoint of the radius is on the circle, okay, at that point, you're going to have that line being tangent. So basically, this is the converse to Theorem 10.1. Okay, so you're just reversing it. Okay, so write those two down in your own words, and then make sure you draw the picture of what you get, or what you have, and then what you get, okay? So I'm going to take a second and go back to this example. Okay, so if I'm looking at this, I'm thinking that I know AB is my radius, and actually AD is also a radius as well. So I'm going to label that as 7 because those will be congruent. And then I'm going to think, okay, since AB is my radius, and I'm looking at CB, and right now it's not making full sense because I'm not seeing my full segment, so I'm just going to go ahead and extend the line. And now I see that I have my tangent, okay? So now I see fully why that AB and CB are perpendicular, because I have my tangent line and my radii meeting, forming that right angle. So I notice I have a right triangle, so I can simply take 7 squared plus 9 squared, set it equal to, parentheses are very important here, 7 plus x and square it. So pause this, solve this, and then we'll talk about the answer tomorrow in class. Okay? All right, next up, let's look at using the converse. Okay? So we need to make sure that I have a tangent line and I have a radius. I need to make sure that those two are going to be perpendicular. So the converse says if the line is perpendicular to the radius of a circle at its endpoint on the circle, then the line is tangent to the circle. Okay, so let's prove that. Well, here, ultimately, I'm just going to prove that I have a right triangle. That's pretty much what this comes down to. So in blue, I need to prove that, let's make a better right angle, that is going to be a right angle. So if you think about it, we've known how to do this for the past couple weeks now after dealing with chapter 9. So I'm going to set up 11 squared plus 60 squared. Is that equal to 61 squared? So I'm going to work through that and see if that is going to be equal to each other. And if it is, then I know I'm going to have the converse to 10-1. I'm going to have 10-2. Okay? So work through that, and we're going to talk about that answer tomorrow in class. Okay? Okay, one more theorem here. It says that if you have two segments now, two segments coming from the same exterior point, so the exterior point is out here, if I have those two segments both being tangent, okay, so clearly I'm not drawing a super straight line here, okay, and I can extend these tangent lines. If those are tangent to a circle and they meet at the same point that's on the outside of the circle, then they're congruent. Then those two segments are congruent. And one other side note, don't I know that these radii will also be congruent? So I'm going to be able to use a lot of these ideas to get segments that are going to be congruent, and ultimately I'm going to show that, I'm going to have some things with triangles that are going to be the same as well. Okay? So write that down in your own words on your note sheet. Okay? And then work through this example. So you have, it says AB and BD are tangent to circle C. Okay, so if they're tangent, that means they're hitting the circle at one point. And then we just need to find the value of x. Okay, so if they're both hitting B, because you see that B is in common with both of those segments, and you know that they're only hitting the circle once, these guys are going to be congruent. So if they're congruent, they're going to be set equal to each other. So then I want you to go ahead and solve that and see what we all get tomorrow in class. Okay, so hopefully this is making some sense. The theorems are pretty, pretty logical if we think about it. Okay? One last thing I want you guys to try tonight is this proof. So do this on the back of the note sheet that you had. Just a simple proof. LM and MN are tangent to circle O. Okay, so if those are tangent to circle O, we know something about point M then, because it's in common with both, so that will imply something. We need to prove what's in blue here. We need to prove that LM and MN are in fact congruent. So you're basically proving your last theorem 10-3. Okay, so I want you to try this tonight on your own. Okay, so hopefully you can go back, rewind, pause, whatever you need to do to fill out that note sheet, and then make sure we're writing down any questions that come up, something that's not super clear to us, and then bring those questions to class tomorrow, and we will work on our assignment and clear up any confusion. Okay, thank you guys for viewing this. We'll see you tomorrow.